Well, welcome back to another episode of Parker's Pensées. This is a podcast where we explore thoughts in philosophy, theology, nature, and life. I love thinking about cool stuff, so come think with me. Today I have another special guest, but before we jump in, I just want to thank everyone on Patreon and everyone who supports me on Anchor. You guys are awesome. You guys are making it happen. If you are listening and you're not a supporter and you like the show, consider supporting me. Buy a mug from the link in the description, buy a sweatshirt, do something. That would be awesome. But without further ado, today's guest is a recurring guest. He's a return guest and hopefully becomes a recurring guest. And we're going to be talking about all sorts of physics and time travel and light, speed of light kind of stuff. So if you've listened before, then you'll know my next guest here is Sean Ressler. Sean, thanks so much for coming on the podcast, man.
Yes, I'm so glad to be back.
You're one of my favorites here because you look so young, man. You look like super young, and you have a PhD, and you're like, can you explain what do you call yourself? Are you a research? What do you call yourself?
Postdoc. So postdoctoral
Okay.
researcher or just postdoc.
Okay, yeah, I didn't know if you guys use that terminology too. Okay, so you're a postdoc researcher, and you're continuing to research black holes and black hole accretion. Is that right?
Yes.
Okay.
Using computer simulations mainly.
Yes, dude, that's what I didn't know. So we were talking before this, and you said most of what you do is using computer simulations. Uh, like, what does that look like? What are you doing?
It's a lot of coding. Well, there's different stages of every project. It always starts out like coding,
Okay,
hardcore, like if then else, blah blah blah, like all
and
that.
that's making the simulation. That's making like the simulated world or whatever. It's
Yeah, so it basically you put in all the equations of physics that are relevant to the problem,
okay.
and then you let a computer solve it because these equations together are so complicated that there's like one analytic solution that's not useful for anything.
Yeah.
And so you give them the equations, you put in some initial conditions like start, I don't know, there's like a bunch of gas surrounding a black hole and you let it go, and then the simulation just goes forward in time. And then so you get data at every so often, it dumps out a bunch of data and you look at it. So it depends on what stage of the project that you're in. It's either like coding, which for me, it's not actually writing the whole simulation. A bunch of other much smarter and more meticulous people have done that.
Yeah.
So there's a bunch of codes available either publicly or privately. The ones I'm using are public. And so like people very well trusted, very meticulous, very well tested code. And then you add your own flavor to it. So you add a bunch of extra physics, or you just adapt it to the problem that you want and you run it. And so running it involves like you get time on supercomputers. So the government owns a bunch of supercomputers all over the country.
Mm-hmm.
So there's like one in Texas that I'm using right now. And so it's like you submit, you like say, okay, well, the simulation itself would take like longer than the lifetime of me if it was just on one computer.
Yeah.
So like many lifetimes for me. Like it would be like my great grandchildren would be like finally get the results, and they'll be like, oh crap, there was a bug.
Yeah.
What a waste. So you divide it up between a bunch of different computers. So generally, it's like thousands of computers. They're all working at once, communicating. Okay. And so then you run it, you wait a little bit, you check in on it, see if it's doing something reasonable, and then you look at the data, and then that's the part that takes the longest. It's like running it and coding is it's fun. It's sort of fun. It depends on how you're always debugging. So it depends on how annoying the bug is, whether it's like some technical thing or something that's more enlightening. But then there's the analysis phase, which is also fun, but it's the hardest.
Is that interpretation? Is that you looking at?
Exactly. Okay. So it's like taking up, like I describe it as like looking at clouds. Like if you're looking up in the sky at clouds and you're thinking like, it just looks like a bunch of random stuff, unless you like have like an artistic mind and you like look at it deeply, and then you're like, oh, that actually really looks like a dog. And so you like, you look at it more and more, and you describe how it really like keep finding more ways that it looks like a dog. And then you like write up, okay, this is why it looks like a dog. This is how it looks like a dog. You put a paper out, but then there's other people that'll look at it. Actually, that looks kind of like a cat to me. Blah, blah, blah. Like, so there's some human element there.
Okay.
But the data, what I'm trying to say is that the data is like really complicated.
Mm-hmm.
So you have to really figure out what you want to look at. And so what ends up happening is that you have this data and you're like, what if I plot this versus this? Oh, that's nonsense. What if I plot this versus this versus this? Oh, that kind of looks like something. But usually you have to have some kind of idea of what's going on. And that tells you what to look at, what to plot.
Okay.
And then there's always a point. You're like, this is a mess. This is a mess. Oh, I plot everything versus everything. Nothing makes that much sense. This weird thing's happening. And then like something clicks and you have the right interpretation, or at least a interpretation. And you can all start like taking the chaos and make it into this nice paper. And you just write it out, describe it. Of course, you're honest about everything you did. Like I'm not 100% sure that this is what's going on, but seems to be the best evidence. And then I like that part a lot. Like once you have the idea and then you're sort of just, it's sort of like I'm bad at analogies. I'm going to make a bad analogy. But cooking, I always think of like you're creating order from chaos with cooking.
Yeah.
You have all these ingredients all over the place. And I feel like there's like a time ticking down and you have to like organize all these things into this neat little package before the time runs out.
That's good. That's good analogy.
I think about it.
Yeah, I like that. You so far you've used clouds and cooking, man. You're on a roll. Well, so many questions from that. Just we'll get into the more stuff, the stuff we planned on talking about. But like, why is someone putting free? Why are people making their code public? Like, why would they do that? Just for the good of humanity?
I guess that's the hopeful interpretation. I think so. I mean, because they still like when they put their code out, then they get like 8 billion citations if it's
nice. And that's good.
That benefits them. But really it is kind of selfless, the people that work on it a lot. Because they're constantly updating it, constantly undoing some bugs that were like in there that only one person ever used that particular part of the code, so they found this bug and they'll be like, okay, let's fix this. And then they spend all this time on it, but that you can't write a paper about just that most of the time. There'll be usually like one paper that describes the code, but then they spend like years and years and years updating this code so that other people can use it.
Wow.
So like everybody else is using their code, doing science, publishing papers, getting academic like status.
Yeah.
And some of these people, not that they're not also getting status, but they're sort of like underground and they don't have as many publications because they're working on the code like full time. So like some of the people have tenure, so it doesn't really matter. They just enjoy doing that kind of thing. Others are grad students. So they got to always strike the right balance between doing the code, like updating this code and doing science.
Yeah.
So I feel like I would enjoy doing it, but I'm also at the same time be like, should I be doing, like, why is this bad for my career to be working on this code so much?
Right.
So I'm not exactly sure their motivation, but they all seem to be very generous with their time.
Seriously.
Maybe they are just the best of humanity.
Yeah, maybe that's it. Well,
they all go. This is like the modern day Gandhi.
Yeah. Yeah, someone's gonna be upset by that. But what system do you use? I don't know a ton, but some of my guys are like Mackies, the guys I disciple, and they'll tell me about like Apple Pie and stuff like this. Are you using one of those like programs to?
I don't know what Apple Pie is, other than
maybe I'm getting it wrong, but I think it's a coding language.
Okay. Yeah, thing. So I'm not familiar with that. So this code is just written in like C++.
Okay, I've heard of that.
And then all the analysis I do is in Python. So everybody uses Python for analysis.
Okay.
And C++ and C are generally the standard for simulations because they're faster.
Okay.
So Python is very easy to use. It's nice. It has prepackaged stuff, but it's very, very slow.
Okay.
If you run a simulation on there, you'd be having a bad time.
Yeah, that's why the supercomputers come in handy.
Yeah. So,
well, how are you getting like? It's so weird that the government owns them and they let people use them, but you just put in like you put in like a request and they let you do it.
I just submitted one on Friday. So me and Chris White at Princeton now, and then a couple of professors. So so I'm the lead author, even just because like the way there's this It's a pain actually doing this because they always find these dumb problems with your proposal that are irrelevant to what you want to do. Like,
Yeah.
oh, you're on this proposal. This other guy's on this proposal with the same people. Why didn't you merge your proposals? You should have just had one proposal together. So instead, we're just going to cut your proposal in half. It's like, okay, how is that helping?
Yeah.
But so we had to combine our proposal, but then he's actually asking for like at least twice as much time as I am. So it's kind of, but it's like this mashed together proposal. But you write this proposal, you say, I have this code, I want to do this for this scientific reason. So we'll be able to publish some papers about this stuff. And then you say, I have this code and it runs really well on your system in a way that it scales very well, which that means if you run it on one computer, if you run it on 2 computers, if you run it on 10 computers, it scales like it goes twice as fast, 10 times as fast, like you would expect.
Yeah.
Otherwise, they'll be like, oh, you're just wasting our, like, you're running on 100 computers, but it's the same speed as running on 10. What are you doing?
Yeah. Dang, that's so interesting. So I had no idea you'd have to do so much computer science stuff. And then
Yes.
you got interpretation, and it's people who are used to looking at the same clouds that you're looking at, and they tell you whether you're right or wrong. Is that through the peer review process? Like, are they able to look at the simulations you ran, or do they just look at the data?
In practice, sometimes we exchange data, but it's usually more collaborative than like, oh, I want to see what wrong you're doing, and just like to check. Like, for instance, if you're trying to check 2 different codes and see if they get the same result, then you share your data.
Yeah.
Like, there are a couple of papers that do that.
Okay.
But usually it's like, we ran this simulation of this type, and then we ran this simulation that is sort of similar but used different methods, and we got this result, and there may or may not be the same. And then you sort of debate within the paper about why there are differences.
Okay.
Which is usually very annoying. You have to figure out exactly why they differ, even though they seem to be basically the same thing.
Yeah. Dang, man. Yeah, this stuff's crazy. It's all crazy to me, but not as crazy as like the one-way speed of light that we were talking about before. So let's jump in. That's my segue. Let's jump into the one-way speed of light. You've kind of looked into a little bit of this since we've last talked. Is that right?
Yes.
Okay, because I'm not super great at laying it out for us. So it's my understanding that you cannot measure the one-way speed of light.
That is true.
Okay, so would you agree with that?
Yes.
Okay.
To our current knowledge.
Okay.
And I have to be honest, when you said this, and then I started looking it up right afterwards, I was like, this has to be like some crazy thing that's some.
Yeah, man. I was hoping. Yeah.
No way. I was like, whoa, wait a second.
It's crazy. It's crazy. When I first heard it too, I heard it from a Christian apologist, and I was like,
yeah,
all
it's
right, man.
One of the things that a Christian apologist would bring up, like they had no idea what they were talking about, but like.
Right. And so I was like, there's no way. So I'm asking you, and then you were like, I don't know what you're talking about. So yeah, so it is like a real thing. Can you explain, are you able to explain why that is? Why we can't?
So. I'll try.
Okay.
I believe I understood it about 2 nights ago, which is like when I had the actual realization about why.
Yeah.
So the basic issue is that you can't really know what is happening right now at a different place in space. So if the only reason we seem simultaneous right now is because we're communicating via light signals or whatever the heck computers communicate with, so that we're synced up.
Yeah.
But there's no real way that I can compare with your clock with my clock without that communication. And that communication is always going to involve light.
Yes.
Because that's the fastest way that you can communicate.
Yeah.
So when you're trying to say, okay, this is happening now where you are, and this is now where I am, you have to make an assumption about the speed of light in terms of whether it's the same as if it was going one way or a round trip.
Yeah.
Because round trip speed you can easily measure, easily measure by, because you're at the same place. You know when it left, and you know when it comes back. So as long as you know the distance between 2 things, then you know how long it took it to go there and back. So you can say, okay, that's twice the distance divided by the time that it took it to return to the same spot. That's just the speed of light. But then you could say, well, what if the speed of light depends on either direction that it's going, or it depends on space? Like, what if it gets slower as it goes, and then it gets faster, just in a way that would take the same amount of time to go back and forth as if it was going at one speed the whole time.
Yeah.
And there's no actual way. So first, you can think about trying to do this just literally measuring the speed of light, like going from one spot to another spot.
Mm-hmm.
And any experiment that you try to set up that will do that ends up involving using light signals to communicate what time this hit the second hand to tell the first hand what time that was.
Yeah.
So you're using the thing that you're trying to measure in order to measure the thing that you're trying to measure. So you can't do that. Like it basically all cancels out, and there's no way to measure the speed of light that way.
Yeah.
And I said, oh, but you don't have to do that. There's this thing called the Doppler shift. So the Doppler shift is light is moving, or the source of light is moving. And so if it's moving very fast, close to the speed of light, the light that was emitted at some frequency is going to appear, or it's going to be absorbed at a higher frequency, because it's sort of like the wave is getting pushed together by the moving thing. In the same way with a car.
Okay.
Like the Doppler shift also happens with sound.
Yeah. Okay. That's I know it. Yeah.
Higher frequency, and a horn going away from you has a lower frequency.
This is when the ice cream man drives past you and you hear the pitch change.
That kind of thing. Yeah. Or the fire truck.
Yeah.
And so that happens with light too, as long as you're going close to the speed of light. So my idea, it's wrong, but this is what my idea was, is that, okay, well, can't you just measure the Doppler shift then? Because if the speed of light is infinite or something in one direction, there would never be a Doppler shift, because you would never be able to go fast enough that your speed was comparable to the light.
Mm-hmm.
And so it would always just basically be the same frequency. But then in the other direction, you would get a Doppler shift because the speed of light was slower. So your speed would be able to catch up, or at least get close to the speed of light. So you have this Doppler shift.
Yeah.
There was actually an experiment. I looked at this. There was an experiment where you had a beam of light, a laser on like a wheel,
mm-hmm.
and you go around really fast on this wheel. And if the speed of light depended on what direction you were going, you would get different Doppler shifts depending on where, because there was like an observer all around, something to absorb the light. And so you would get a different frequency at every point if there was any dependence on if the speed of light was different in any direction. So they did that, and they found no noticeable difference. But then another paper pointed out that there was a problem there. So the problem is that the time, it's again this thing, you don't really know when now is. Okay. And so, like if you imagine something is 1,000 light years away, which is to say let's say 1 light year, that's easiest. 1 light year away. So light, if it traveled at a constant speed in every direction, would take 1 year to get here. Mm-hmm. So you observe a signal here from a light signal, and it says, okay, I'm leaving right now. Like the spaceship is there. It says, I'm leaving right now. So, and then it gets here in like 0.99 years, or no, 0.99 years. So it's traveling very close to what we would say is the speed of light. And so, but we say, okay, it left 1 year ago because that's when we got the signal, and it got here 1 year later from there. But then if the speed of light in that direction was infinite, actually, even though you thought it was the regular speed of light, that signal would have actually been emitted just when you got it. So not 1 year ago.
Yeah, it would have happened instantaneously.
Yeah, but then that object traveled that amount of distance in a much shorter amount of time than you figured.
Right.
You thought that happened a year ago, but that actually happened like just now.
Yeah.
And yet the object just got to you anyway. So what ends up happening is that in this interpretation, all these velocities sort of scale up with the speed of light, so that all the physics is the same. At least that's how I understand it.
Yeah.
It's
okay.
I think like a redefinition of time itself, instead of like actually, because it's almost the idea is that measuring a speed is almost arbitrary when the speed of light is something that you're not assuming to be something.
Yeah. Because the speed of light is so important for all of our measurements.
So I think the idea is that everything, if you just assume that the speed of light is the same in every direction, all the physics, all the results that you get are exactly the same as if the speed of light in one direction was infinite and the other direction was half the speed of light. There's no way to actually measure that. Just the way special relativity works.
So it doesn't really affect.
I don't know if that was a good explanation. It's sort of like it's just blossoming in my brain because I was like, the Doppler shift has to be. It has to be. You have to be able to measure this. But the reason I was confused is because I was thinking about if the speed of light was infinite everywhere, because then everything, special relativity doesn't matter anymore. It's just like Newtonian physics.
Yeah.
But it matters that it's not just that it's infinite everywhere, but it's infinite in one particular direction, and then it's regular or half of the speed in the other direction.
Yeah. And when you say infinite, I think of like instantaneous. Like same. That's what you mean, right?
Yeah.
Okay. Yeah, infinite. Okay, which is crazy because it wouldn't, as long as we still have like the round trip and we just divide that by 2 and assume that's the speed of light, then all of our stuff still works. So it doesn't like mess with any of our physics.
Nope.
It just means like we can never actually know the one-way speed of light because it might be different leaving its source than coming to its source. It might go from its source to wherever it's going instantaneously, but then take twice the speed of light to come back. And so when we divide that by 2, it still looks like our one-way speed of light through our mathematics, but we can't actually measure it.
Even then, you have to be a little careful about the language you're using.
Okay.
Because even saying it's instantaneous is like you're still assuming something about what time is, about when is now. It's almost like it's not. I'm not sure if this distinction makes sense, but it's like.
Okay.
Like you think about the speed of light being infinite as if everything else is the same and the speed of light is just infinite. But it's actually, the speed of light is infinite, and then like all the other velocities and times change as well. So velocity is no longer what you would think of as velocity. It's going to be this thing that seems like it's much faster than you would have ordinarily assumed.
If the speed of light is infinite?
Yeah. Because it's not just taking the known physics and then making the speed of light infinite. It's sort of like all the physics sort of scales with the speed of light, if that makes sense.
Yeah.
Like the speed of light is now 10 times faster, but all the velocities are 10 times faster. Not exactly 10 times, but the idea.
Yeah, it would
so
scale
it's almost
up.
like it doesn't really make any difference.
Yeah, okay.
Yeah.
Which is all crazy because you would think we can observe this and that, we can look at some changes, but no, it would all scale along with it.
Yeah.
And so you really just cannot, at least from what people think today, like you cannot know the actual one-way speed of light.
Yeah.
Which is nuts. That's crazy.
Yeah.
Well, and it's because of special relativity or general. Yeah. Is it which one?
Relativity.
Special. Okay. Yeah. And we talked a little bit about that, but can you fill us in again? Like what's special?
So just to define what special relativity is, it starts from 2 postulates that Einstein came up with.
Mm-hmm.
So the first is the physics. Physics is the same when you're in an inertial reference frame, no matter what that inertial reference frame is. An inertial reference frame is a reference frame that is not subject to forces or acceleration.
Is this a vacuum or?
No, if you're like, I'm in an inertial frame right now. Well, technically I'm not, but because the Earth is accelerating. But like a stationary frame, a frame moving at constant velocity, and when you're in a car and you turn really fast and you get jerked to the side, that's not an inertial reference frame.
Right.
Because otherwise you would be like, what's the force pushing me to the right? That doesn't make any sense. Because if you think of yourself as in the car stationary frame, that if you thought about it as an inertial frame, that force would be like some strange weird force, but it's actually a fictitious force because the car itself is accelerating.
Yeah.
Or like in an elevator when you go up and you feel yourself being pushed down.
Yeah.
At least at the beginning.
Yeah.
So it's a frame where like all the physics is the same, basically.
Okay, that makes sense. And what's that called again? An inertial
reference frame. So if you're traveling in a car at a constant speed and there's a parked car next to you, there's no difference in the physics whether you're the one moving and the car is stationary or the car is actually moving backwards and you're stationary.
Okay.
There's no difference in terms of physics.
Sweet.
Okay. And then the second one is that the speed of light is constant in all frames. And so that's not exactly something that you would intuit. That's very strange, because you would think, okay, if the speed of light is, say, 10 meters per second, it's much faster than that, but it's like 10 meters per second, and you were able to go 10 meters per second, it would look like the light was just sitting next to you, because you'd be going at full speed. Or you could even go faster than it, that it would look like it was going backwards, or you could at least make it go slower or something.
Yeah.
But Einstein had this thought experiment. What if you were to catch up with the speed of light? What would it look like? But then you have to think about what light is. So what it is it's an electromagnetic wave, which is an electric field that's just oscillating. It's going up and down. It's moving up in time. And because of Maxwell's equations, which describe electricity and magnetism, which are both sort of the same thing, the time change in the electric field causes there to be a magnetic field that's like sort of perpendicular to it. And that also oscillates with the electric field. I can't do this with my hands. This is like the I don't know, pat your stomach.
Yeah.
But you have like one's oscillating like this, one's oscillating like this. And the electric field going up and down causes the magnetic, like it creates this magnetic field.
Okay.
Because they're changing.
Yeah.
But if you were to catch up with it, they wouldn't be going up and down. They'd just be stationary, because they wouldn't be moving anymore.
Yeah.
And so they'd be stationary, but according to Maxwell's equations, then there wouldn't be any wave and there wouldn't be any light. So it's almost like a contradiction.
Whoa.
And so Einstein's like, this can't be. This can't be. He was like really upset about this. He was like, I don't know, he's like 18 or something, maybe 20.
Yeah.
He's like, it can't be. And they had all these weird ideas about like ether and stuff.
Yeah, I remember
like,
that.
No, this on principle, I think this can't happen. So the speed of light must be constant no matter what speed you're going. And so that was his idea. And then he derived all the stuff that comes out of that. So those are the two postulates.
Okay.
And that creates special relativity.
And most physicists are like, this is what's up, right? Are there people doubting special relativity today?
Not in terms of like any, like if people are doubting it, they're downing it in like the really fundamental level where like, oh, maybe it's like a quantum theory of gravity or something.
Sure.
But for the scale that we observe on a day-to-day basis, it's like gospel basically.
Okay. So, man, what is traveling at the speed of light? You said it's a wave, but is it like photons? Is it electrons? Like if you were to pull up next,
no,
I think
it's photon is just a word for the electromagnetic wave.
Okay.
But it comes in like packets. So like a photon is a packet of this wave.
Okay.
But that's all it is. It's electric and magnetic field, which is what makes it special in that sense. Because it's traveling through nothing. It's just this field that causes.
Isn't the packet like traveling through space?
Yeah, but the space has nothing in it.
Okay.
Well, it could have something in it, but in principle, it doesn't have to have anything in it.
Are photons made of electrons? Or are they smaller than electrons?
No, they're made of they don't have any mass or anything.
Whoa. Okay.
These fields.
Wow. Oh yeah. Okay. Wow.
Yeah. So you could say, oh, it's a photon, but a photon is just the electromagnetic wave. So it's sort of like just defining it.
How about when we get hit with rays from the sun?
Yeah, so that's a photon, or that's light wave.
So it's light wave, but like that goes into my skin and heats it up. Yeah.
So it's just energy.
Okay.
It's massless energy that travels through space.
How about neutrinos? What are neutrinos?
They do have mass, or at least we think they have mass. We don't know the exact mass.
Okay.
There's there's a difference in mass between some of them. That's what we can measure, I think.
And do neutrinos have like spin or anything like that?
Yes, I believe so. I think so. I think they must. They must have spin. Because photons have spin.
Photons have spin?
Yeah.
Oh, I didn't know that.
They have integer spins, as opposed to like electrons, which have half spin. Which it's also a convention. You could say, oh, the electron has 1, while the photon has 2, or something.
Okay. Well, because electrons freak me out, right? Because there's like the wave versus particle debate, and there's the collapse of the wave function. So in my head, I'm thinking like photons are like a wave packet type thing,
Yeah.
And that seems to me really similar to like an electron, which is like this wave.
Yes. In that sense, there's not, because they're both fundamentally described by a wave function
Yeah.
from like Schrodinger's equation,
Yeah.
which is the quantum mechanics basic equation.
Okay.
It
Yeah.
just describes how a particle, like a particle is not really a particle. It's like a probability distribution of
Yeah.
an electron's existence.
It's like a cloud, right? It's
Yeah.
like, well, and that packet language kind of reminds me of the same thing. It's like you think you have this electron, but it's really like this. It's here, and it's somewhere in that little like
Yeah.
packet, until you look at it, and then apparently you can
Yeah.
make it in one spot.
So I know I have colleagues that feel very strongly about the collapse of the wave function now being a bunch of BS.
Yeah,
So I won't comment on that because I've never listened to their argument long enough to understand why they think it's BS.
I hope it is. I don't like the collapse of the wave function stuff. That it freaks me out. And it's all this. It opens the door for all this weird woo woo stuff. I just wrote a paper on the simulation theory,
Mm-hmm.
and actually one of the dudes. It's really fascinating. He's a computer scientist, Rizwan Virk, and he says, yeah, the collapse of the wave function actually makes sense if we're living in a computer game, because if you look at any kind of computer game, they don't need to render the whole world. They only render where you're looking. And so when you look over to the right, that didn't actually exist, that part of the map, but it renders once you look there. And he's saying, yeah, it's probably the same thing with electrons. They're a wave until you observe them, and then they collapse down into a particle. And it's like, that's really interesting, actually. And I hate that you said that. I don't like that. That's so weird. And there's other reasons to not believe you're in a computer simulation, but that's one of the things that they're saying. Yeah, computer simulation is a theory of everything because it can unify Einsteinian and quantum physics. Well, it's pretty popular level, and it's
Yeah,
pretty just
no, yeah, I know. I've heard a lot about it.
okay.
And a lot of people that like to. I mean, I know that Rogan loves to talk about it, and like I think Elon Musk, and there's also the guy who wrote Dilbert is also a big fan of it.
Oh yeah, man. Yeah, it's the thing. It's funny because you're like, hey man, let me tell you about my faith a little bit. So I believe God made the God, what are you talking about, dude? You're so stupid. And it's like, well, what do you think, man? Well, obviously we live in a computer simulation and there's a simulator. And you're like, well, was the simulator like a person like us? And they go, yeah. And then you're like, well, who made that simulator? Or they're like, no, it's not like us. It's like this immaterial thing that's like a genius. And I'm like, well, that sounds a little bit more like God, though. It's a fun
Yeah,
conversation. I do like it. Yeah, we're gonna do an episode on that here coming up. But okay, so dude, you're blowing my mind with the photon stuff. Is this so you work on like the grand scale though? You're working on like big black holes and stuff, right?
yeah.
Do you deal with this kind of small stuff that often, like photons? Okay. Well, that's
Well,
cool.
yes. So when you do, so usually I run simulations that are just like hydro or magneto hydrodynamics.
That's the coolest thing I've ever heard. That's
So
awesome.
if you want to hear it, it's really the whole thing is general relativistic magneto hydrodynamics.
That's so cool. That magneto is epic, dude. That's
Yeah, I
great.
know.
That's magnetism, something with
Yeah,
magnetism.
it's just magnetic fields plus fluid dynamics.
Okay. That's
And
sweet.
then after the fact, after you run the simulation, you can calculate the light that gets emitted from that because it's a bunch of hot electrons. So what creates light is moving electrons or accelerating electrons.
Yeah. Okay.
You're a charged particle, but electrons accelerate much faster because they have less mass.
Yes. Okay. That's why I wanted to bring them in. So okay, dude. Electrons, they're going really fast. Do they send out like a photon or what?
Yes.
Where does that photon energy come from?
It comes from the energy of the electron.
And when the electron has to lose that energy, right? It's not just coming out of nowhere.
So
Okay.
sometimes it becomes from the electron is bound to an atom and it has discrete energy levels. Like this is like the quantum, or not quantum. Well, it is quantum, but it's the stuff you learn in like chemistry 101 in college, maybe high school, where they're like energy levels and you're like, what are these energy levels? I don't know. Shut up. It's an
Yeah.
energy level. And then so they jump from an higher energy
Oh
level to
yeah.
a lower energy level, and that's where the photon of exactly that energy gets emitted.
Yeah. It releases. Yeah. 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 I remember that part of it. I remember the jumping.
Yeah.
Yeah.
So other ways that it can emit electrons, if it's like a free electron, it's just moving all over, and any acceleration of that will cause it to radiate. So radiate, in other words, create a photon.
is there some? I'm sure there's probably like a calculation so you can say like a electron with this charge or whatever, like moving that's free is going to lose all its energy by this
Yeah,
time. Is that
yeah,
possible?
exactly. Yeah,
Okay, nice,
like, it
dude.
depends on the radiation mechanism. Like there's like the one way is what's called synchrotron, which is an electric field, or there's a magnetic field, and the electron, because of the magnetic field, it just spirals around the magnetic field like this.
Yeah, yeah, yeah.
And the whole time it's emitting radiation, so it's like spiraling less and less and less and less. And so
Okay.
when you said the time, it's called like the cooling time, or like the synchrotron cooling time, or something like that.
Yeah. Dang. Okay. Well, do you know any? Do you know a little bit about magnets then too?
Sort of
Okay.
depends on
Well,
what you want to know about
well,
magnets. I
dude.
can say
Okay.
yes until you ask me something that I don't know.
Yeah, yeah, yeah. So when I was a kid, I was obsessed with like Sharper Image. Do you remember Sharper Image stuff?
That sounds very familiar.
It's like this store with just useless stuff, but it looks really cool, like a pen that does this weird thing. I had
Okay.
this thing called like the Gravitron, I think. And it's like a top and you put it it's got like this base that's made of magnets. You can't see, it's really slick looking. And
Yeah.
it's just got a like a pen point that goes against some glass to kind of keep it there. Otherwise, it would keep going that way because the magnets in the thing and the magnets in the base. So it's like basically just think of like a pen and a base, and the
Yeah.
pen's hitting there and it's spinning by itself. And you spin it and it just floats. And it's super cool. Like, dude, where's that magnet getting its charge from?
Right. So it's not charge.
Okay.
It's so
It's force.
charges create electric fields, but
Okay.
there is charge, but moving charges create magnetic fields.
Moving charges create magnetic
Yeah.
fields. Okay.
Stationary charges create electric fields. Moving charges create electric fields and magnetic fields.
Okay.
But yeah, but in general, magnetic fields are easier to create because
Okay.
you need an exposed charge, which is very hard to maintain because if you have a bunch of positive charge, negative charge will snap onto it, just like
Oh,
when you
it's
get shocked.
neutral.
Yeah, when you get shocked, that's
Yeah.
just the electrons like, oh, I want to be neutral.
Okay.
I'm poking wood, so it's not working. But
Yeah.
yeah, so there it's like the electrons in the metal, in these metals,
Yeah.
have like this. They sort of have their own little motion, and so they have like this little bit of magnetism. And in a magnet, so each one has like a little vector of a magnetic field.
Okay.
In a lot of metals, those are all random.
Yeah.
But in a magnet, you get it so that they're all frozen in like exactly the same direction.
Yeah.
It all builds up to like a coherent big magnetic force,
Cool.
and that's
Well,
generally what happens.
how do you
There's no electric field because there's also protons in there. So the protons cancel out the otherwise there would be an electric field as well, but there are also protons. So
okay.
there's no net charge, but there's this magnetic field because the charges are moving.
Well, how would you get all the vectors to point in the same direction?
I forget how you do it.
Something through electricity, probably.
Yeah, I think you got to you put it through an external magnetic field, and so all the little vectors will align. I think you heat it up, and so they're more free to move.
Sure.
And put it in a magnetic field, and they all align, and then you cool it down.
It sounds right.
That's something that I remember.
Dang, that's so cool. It's so weird. It used to bother me so bad that we were made of electrons and stuff because I think like I'm a solid, dude. Come on. Yeah. But then, and when I first learned about neutrinos, it drove me insane because all these little things passing through me. But
dark matter's doing the same thing. So,
what'd you say?
I said, well, dark matter is probably doing.
Yeah. And then we get to dark matter, man. Like, we talked about Fermilab before, right? Have we? So one of my friends works at Fermilab as he's like an environmentalist there. So he like checks all the water and makes sure Fermi's not like dumping anything or anything like that. And it's a sweet job, but he went through and
numbers when they are dumping something.
Yeah. Yeah, you just gotta
oh wow, that's bad.
Just cover that up, put some dirt over that part. But so last time I was there, he gave me like a tour, and they're really big into dark matter. They want to be like the number one force or the number one studying whatever research place on dark matter. And so I'm getting all excited about it. They're sending dark matter or something underground to like a mine in Minnesota, and they're like, it's crazy because you can send it through the earth or whatever. And then I was all pumped up about it. I put it on Facebook, and someone was like, "Yeah, I guess if you believe in dark matter." And I was like, "What?" And then it turns out that's something people are really strong about. They feel real strong about, that there is no dark matter. Have you heard of that? There's people who think dark matter is a hoax.
No, but I've heard about people who think the Earth is flat. So there's
Okay.
not a big stretch to
But
him.
so, dark matter is a thing. You believe it's for real.
It's a thing in the sense that there's a bunch of stuff that's dark that we don't see that interacts gravitationally.
Yeah, and you can see because of its effects, right?
Yeah.
Yeah. Okay. Okay.
I mean, I've had crack. Well, so one of the best things about ever doing anything that's slightly in public is that you'll get crackpot emails as a scientist.
Yeah.
And so one of these guys thought dark matter was a bunch of crap or something. But he didn't understand basic Newtonian gravity that you learn in high school.
Yeah.
He's like, this doesn't make any sense because the objects are orbiting like this, but if you just do GM over R, it the mass doesn't match. And it's like, no, guy, there's this dark matter. The point is that the dark matter is spread. It's not a point mass. It's spread out because the fact that it doesn't interact with anything means that it's very diffuse and it doesn't concentrate.
Yeah, we talked about that.
It's all spread out. So then these galaxies move or the distribution of stars moves in a way that is much different than around a point mass.
Yeah.
But I don't know. I had a great time reading this guy's website. Especially when they're mean is when you can really have fun. It's because if they're also mean, you don't feel bad about making fun of it.
Right.
There are some that are nice. One guy was really concerned about the black hole, about how we're all going to die because of the black hole or something. I was like, actually, the black hole is so far away, it's not really doing anything to us, where the gravitational force is negligible. He's like, thank you. I'm so relieved.
That's great.
I was like, oh, you're welcome.
Yeah. Dark matter to me, when you say it's spread out, I think of a weight blanket. It's weight blankets are weird. Have you ever had any experience with the weight?
I haven't had.
If you ever use one, it's super duper weird because it's everywhere. It's not like if you had a medicine ball on you. It's just everything's heavy. And that's just, I don't know if anyone's listening, maybe that'll help you come up with a concept in your head. But it's diffused out. The weight's all completely spread out and it's just there. And so the planets wouldn't, it's not like if it was circling around a black hole, which would have more of a dense center or something, right? Okay. All right. So this gets us into we're talking relativity. It gets us into time travel and time kind of stuff. And so I've had a couple conversations with philosophers on time, and so now we're talking the physics of time travel and stuff like that. So you sent me a couple of things that you'd be willing to talk about. So presentism, for the listeners who have listened to my conversation with Taylor Sear, you'll know what presentism is. It's basically that what exists is the present. Sean, what do you think about presentism, man? Is that your preferred theory of time?
No. So I think it is completely incompatible with special relativity.
Interesting.
There's no way to reconcile it unless you also say that not only does only the present time exist, but only the present space exists. So that would be you as yourself is the only thing in the universe that is existing right now.
Yeah.
But there is no now. There is no now that is the same for everywhere. And I can so in special relativity, if you have an event happening here and here, and you're both sitting still, and you think that let's say lightning strikes these spots both at the same time.
Yeah.
You're okay, that happened at exactly the same time. I know that is now. But some guy that was going really fast this way, and he passes by as lightning is striking, to him, one of these will happen first.
Yeah.
Lightning will strike here first and then here. And he could also go in a different direction and then he would have the opposite happen. Yeah. So there's this whole smeared out now. It's well, this could be now, but this also could be now.
Yeah.
And this could be now. And in fact, events can happen before or after each other if they're separated by a large enough distance.
Yeah.
So if two events are separated so far that you can't communicate between them, you can't say, okay, this just happened, and send a light beam to the other guy saying, okay, that just happened, now this is going to happen. If that distance is too large, they can happen in any direction or any order.
So the present moment, if presentism were true, would have to be longer than a moment.
Yeah, it would have to be this really fuzzy kind of diffuse, again, using diffuse, like time would be diffuse.
Yeah.
There'd be like this, have you seen the movie The Langoliers?
What's it called?
The Langoliers?
Oh.
It's some like random movie that I had never heard of when I was a kid, and we watched it in my friend's house. He just had this thing. He had the VHS, and it's this really weird thing. They're in an airplane, and suddenly everything's weird. They land, everything's like, it's like the sound is all messed up, and nobody's there. Like people have disappeared from the plane. They're like, "What's going on?" And this is going to be a major spoiler, but this movie probably doesn't even exist anymore. So
yeah, bring it.
It turns out they were like in the past, but there were these things called the Langoliers that were like eating the past. So they were running out of time.
Yeah.
So like but they were in the past, and the present was like still going on, but they were stuck in the past. So there was this like growing length of past, but that was also being eaten up at the back.
Yeah.
So maybe that's how you could think about it, is like the past. There's like this interval that exists, but like these Langoliers are coming and eating the past, and the present is just, and the pushing forward into the future or something.
Yeah. That's good. I like the Langoliers thing. That's something that like a philosopher might hear, and they'll make like that'll be the title of the next paper.
Yeah,
that'd be good, man.
there was some weird guy the whole time, like tearing newspaper strips and like having a nervous breakdown, like the entire movie.
Yeah.
And he was like, "It's the Langoliers. My mom always told me about them, and they scared me." And then I don't know. It's such a weird movie.
Someone's got to introduce
like a famous director. I don't know, or from a it might be like a Stephen King story or something.
Okay, it's definitely interesting. Yeah, it's weird, but time
more about whether there was actually a limit to what could be now. Like if you're arbitrarily far away, you might be able to be arbitrarily far in the past. Like if depending on what frame you're in, like it could be, you could be say that's now, but then somebody going really fast could say like that was arbitrarily far in the past.
Yeah.
So I'm not sure how wide this interval might be.
Yeah. Well, because relativity says that time and space are like integrally connected, that you don't separate them out. And so like on Jupiter, time is faster or slower? Faster. Because heavier?
It would be slower, yes, because it's heavier. Is it heavier? Yes. But it depends on how far out you are. I don't know what the surface gravity is.
Oh, okay.
It's more massive. It's more massive, but I think it's also much bigger in size.
Yeah.
So it could be more massive, but at the surface, you're much farther away. So it might be less gravity.
That's so and as you approach like the center, time would change, kind of like spaghettification or something.
Yeah.
Okay. It's so weird. It's so weird. Okay, so let's talk like external and internal time then.
Yeah. So along the same lines, I don't think there is a way to define external time. It's all a bunch of different internal times that you have to compare in some way. Like every object at every point, or every point has its own internal time, if that makes sense.
Every point does.
Like every point in space, and not even actually every point in space, every frame. So not just a point, but how fast you're moving at that point.
Oh yeah. Okay, so that would be a frame. That would be the point plus the speed.
So there's like an infinite number of frames, and those are all individually could be different times.
Because one frame could include 2 points or something?
Well, one frame is always like localized to a point.
Okay.
And it's moving at some speed. So that's a frame. That's all a frame is. It's like you're at a point and you're moving at a speed.
Well, so
relative to something else.
Wouldn't that be finite because the universe is finite?
No, because there are infinite number of points even within like right here.
There's an infinite? There's an actual... Are you sure?
You could be there, then you could be 0.1 centimeters to the right, or you could be 0.01 centimeters to the right, or it could be 0.001 centimeters to the right, 0.0001, and there's no limit. It's like the number of numbers between 1 and 2. It's
right.
Different levels of infinity.
Yeah. So there's like a debate whether it's like an actual infinity, right? This goes back to like you've heard of like Zeno's paradox and stuff like that from intro to philosophy courses. Those are the best. And Zeno's a rationalist, and he's like, No, motion's all an illusion because things can't move. Right? You shoot an arrow, and at each arrow, or in order for this arrow to get to that bullseye, it has to point. It has to move from point 1 to point 2 to point 3. But in between there, just like you said, there's point there's 0.1, there's 0.2, 0.01. And so it has to actually cross an infinite to get there. And that's illogical. That's crazy. So it must be, let's follow the math here. Let's be mathematicians. And we say, no, motion is illogical. It just looks like things are moving, but we know from our math it's impossible. And so it depends on what you're prioritizing. But that's a good, so you just brought up Zeno's paradox in the infinity of points between your fingers here, which is wild. Which makes motion seem pretty weird. Like Zeno's not crazy, I don't think. I think he was actually really smart. But it's super weird to think that we're like traversing infinites when we take a walk to the fridge.
Yeah.
That's crazy. I haven't looked into that enough. I know there's probably some philosophers out there who are saying I'm totally wrong on that and Zeno's a dummy, but okay, so because there's all these frames, could a frame, I feel like you could have more than one frame for one point, but maybe not.
Oh, yes. Yeah.
You could have, okay, yeah. Cool.
So there's even more than infinite.
Yeah, which is another weird thing, right? It's like there's more.
There's levels of infinity.
Is that technical, or did you just make that up?
It's technical, yeah. It's called cardinality.
Cardinality?
I never studied it very much, but we brought it up. But like cardinality, yeah, like trying to think of an example. Like there's an infinite number of integers, right?
Yeah, so I was hoping to bring this up.
Higher level of infinite number of like real numbers.
Yeah, which is nuts. I just saw that the other day. Yeah, and it's like, well, they're both infinite. Yeah, but one infinity has more numbers than the other infinity. You're like, but they're both infinity. It's like, yeah, but one's bigger. It's so weird.
Buzz Lightyear had it right. To infinity and
beyond. Yeah, he must have been talking. Yeah,
I used to do that in calculus class. I was like this nerdy little kid who never said anything. It was really awkward. But like, if you wrote like the integral, did you take calculus?
No.
Oh, well, you write integrals, and like there's like these symbols, and they have limits. Like it goes from 0 to infinity.
Okay.
I would write like 0 to infinity, and then and beyond infinity.
Did you get laughs out of that one?
I think by like one person maybe. Okay. Yeah, it was like the time in your life when laughs are not determined by like actual comedic value, but by your status in society.
Oh man,
in high school society.
Yeah, that's not
fun. The most hilarious person ever, which I thought I was.
Yeah,
like because I was like a nerdy, unpopular person. Nobody laughed, but really it was because it wasn't that funny.
That stuff drove me insane, though, man. I hated that because I would think about stuff and be like, wait, no, this was like an objectively funny joke, and all of you should have got this because last week we talked about this in class. Like, I don't understand. But it's like, oh, I wasn't tall. Like the tall kids would get all the attention, and they were, oh, that kid's so funny. Like, oh, yeah. I'm glad we're past that, I think. Okay, so we have an internal and external, but this is something that gets me going, dude. The twin paradox.
Yeah,
this is cool. You can tie it all together now.
Yeah.
So do you want to just lay that out for us?
Yeah, the twin paradox. The funny thing about the twin paradox is that nobody ever mentions the paradox part. They mention the part that's weird, but not the paradox. So the twin paradox, you hear about it. You have two twins that are starting on Earth, and one is an astronaut. Well, maybe they're both astronauts, but only one gets to actually go on the journey. Yeah. And one goes on a rocket ship to a faraway planet, traveling close to the speed of light. And then he turns around and he comes back and he reaches home and he finds out that he's actually aged. He's younger now than his twin by a significant amount.
Yeah.
So less time elapsed for him in that sense, his internal time. He had much less internal time than this other guy who just sat on Earth.
Yeah.
He aged more than he did. So it depends on the numbers. Like it could be like 5 to 10 years, 5 to 8 years, whatever. It just depends on how fast you're going. And it could be like a very large, like almost an infinite. I think it is infinitely. The parameter space of how much the guy can age is infinite. Like he could be arbitrarily old or arbitrarily young compared to the other one. So it could be like 5 years versus 10 years, 5 years versus 100 years, 5 years versus 1,000 years.
Oh, okay.
How close you get to the speed of light? Like 0.99 times the speed of light, or 0.999, or 0.99999.
Now, is it impossible to travel the speed of light?
Yes.
Okay. Why is that?
That's the sort of the postulate. Again, that's like the basic postulate. So that would be, if you travel at the speed of light, you would see a stationary light wave, but that doesn't make any sense. In other words, like,
Yeah. Would you be stretched out? Would it be like, because if you were to travel that, would you then have to like become a wave?
no, you would just see light as normal. No
Okay.
matter how fast you're going, it would look the same. That's why relativity is so weird.
Well, Einstein's thing was like, I think I just read this book on Gödel. Do you know anything about Gödel at all? You heard that name? He's a mathematician. He was like young
Oh,
when.
Gödel.
Well, yeah. How do you say it?
Well, no, you're saying it right.
Oh,
I
okay.
just know it as Gödel.
Yeah. Yeah. So because I was reading this book on him, he was friends with Einstein, and they were like these kindred spirits and stuff. And I think Einstein's whole thing was what you said earlier, but it sounded like a little 14-year-old would say, like, if I look over at a photon or look over at light, like what would it be like if I
Yeah,
looked over at it, right?
yeah,
Which is like something that I would. This is great. That's like I can get down with that. I've thought
yeah,
about that. It's cool.
yeah.
But so if you looked over at it, it wouldn't be moving. So he ended up saying that. Explain what he said, because he said it's like it doesn't make sense that you'd look over and it wouldn't be moving, right?
Yeah, because the whole idea of what an electromagnetic wave
Yeah.
is things is an electric field changing in time, creating a magnetic field changing in time. If you don't have either of those components, it's just like a regular stationary electric field.
Yeah, and because
You
there's
need
there
this
in the
motion.
be-
Otherwise, or Maxwell's equations are different in different frames. That were his options were, okay, either Maxwell's equation changes, physics changes in this frame as you go close to the speed of light, or physics doesn't change, but the speed of light is always the same in every frame.
okay. So what does that mean for him looking over at light?
It means that he would never be able to get to that speed.
Can't do it.
So it's
Can't
like
do
a
it.
contradiction.
Okay.
Yeah.
Okay. So yeah. Okay. So you can't travel the speed of light, but you can approach the speed of light
Yeah.
theoretically. Like
Yeah.
we haven't done it or anything, but
Yeah.
so there's this twin, and he's an astronaut, and he's flying out in space, and he comes back, and he might be 10 years younger than his twin on Earth.
Yeah.
And
And
is that the paradoxical part?
no, that's just the weird part.
Okay.
The
Because that's what I've
paradox,
heard. Yeah.
yeah, that's the thing. Nobody ever goes into the paradox. You think
Yeah.
there's no paradox there. It's just weird, right?
Yeah.
There's no logical paradox. But the paradox, or the seeming paradox, is, imagine it from the astronaut's point of view. To him, it just looks like the twin Earth just goes away really fast. He's the guy in the rocket ship's just sitting there, and then the Earth comes back really fast. And the whole time he's looking at the other guy, or the other guy's clock is moving slow with respect to his clock. Because the idea is that moving clocks run slower than stationary clocks.
Yeah. So you give each twin a clock, and then you send them off, and you bring them back, and their clocks are now 5 years off, right?
Yeah.
10 years
But
off.
for both of them, at every point in time, their clocks look like the other one's clock looks like it's going slow.
Yeah.
Because in each one's own frame, they're stationary, the other one's moving fast.
Oh, is that part of it? Can they see each other's clocks?
Yeah.
So there's like
there's two effects. There's the effect of the light propagating, like, because there's finite speed of light. So light is going to take a certain amount of time because he's moving away. It's going to take a little longer or something. There's this effect. But in terms of this paradox, all you need to think about, they got the light and they calculated when the light was emitted.
Yeah.
They like accounted for all that.
Sure.
So the clock would actually be slow. It's not just appears to be slow, but the clock is actually slow in this frame.
Yeah. Yeah, and it doesn't seem. It's just like you're just moving. It's not like any kind of magic going on. I'm just moving, and now this clock is going very slow, but I know that it's not going slow. It's just because of me. So it is like an appearance, but it actually is going slow.
Yeah.
It actually is, but the other twin is like, no, it's not.
Yeah. The twin is like, my clock is normal, your clock is slow. The other twin is, my clock is normal, your clock is slow. They're both right.
Well, does the twin on Earth think that his twin's clock is going faster or slower than his?
Slower.
He thinks his twin's going slower?
Yeah. They both think the other one's is going slow.
Why?
Or they're both right. They don't just think it. They're both right.
Well, why is the why is the one that's moving in space? Why would that appear to be slow, or why would that be going slow?
Because he's going fast compared to the. So it's all relative. It's
Yeah.
all relative to your own frame. So to the guy on Earth, the other guy is going fast, and then he comes back. He's still going fast. So he's going fast, so his clock goes slow. And if you
Okay.
really want an intuitive way to why the clock is going slow, imagine you had a clock that was light traveling in between. Like you count up and down as 1 second.
Uh-huh.
That's 1 second. So you're just bouncing up and down. 1 second, 1 second, 1 second. But now it's moving. So now the light is going like this like to a stationary observer. It's going
Okay.
like this.
Yeah.
So you're saying, okay, every time it goes up and down, that's 1 second. Because the guy sitting stationary, he's just seeing the light go up and down. It's not moving to the side. So him, it's still 1 second, 1 second, 1 second. But to the guy sitting stationary, it looks like light is going diagonal like that.
Yeah. And so now it's covering space as long as.
Yeah. So it goes more distance. So it looks like the time is actually, so what one guy would call 1 second is slower than what the other guy would call 1 second. Light is going the same speed in each person.
But it's covering more space.
Yeah, more distance. Yeah.
Okay. So that makes sense for why the twin on Earth would see the twin in space, the traveling twin's clock to go slow. How about why would the traveling twin see his other twin on Earth? Why would he think that his clock is slow? Why would he see that as being slow?
Because, and it would actually be slow.
Yeah.
Because to him, it just looks like Earth is going away from him. He's just sitting there in his rocket ship. Like if you're in a car watching the trees go by.
Yeah.
The trees are moving really fast in the opposite direction.
Yeah.
So to him, it's just the Earth moving away and then coming back. And Einstein's whole idea is that because he's moving at a constant speed, the physics is the same in both frames. So either way is a valid way of looking at it.
Yeah, because they're both fixed.
Yes.
What are they called again? Fixed
inertial frame.
Inertial frame. Yeah. They're both fixed inertial frame.
Not fixed, but just inertial frame.
Inertial frame. They're both inertial frames because one's traveling at a constant and the other is still traveling at a constant because the Earth is traveling at a constant. Because the Earth, we always assume it's like still. No, it's still, but it's moving at this constant.
Well, it's not moving it's accelerating. But
because it's on ellipses or something.
Compared to like what we're experiencing now, you can effectively treat it as an inertial frame.
Okay. So this is true, but probably imperceptible when you sync up. If you and I were in person syncing up our clocks, but then traveling across the country, that it's still happening. It's just we wouldn't see. Would it even be perceivable? Like, would it be? Yeah. You'd be seconds ahead of me or something.
I measured it to like I don't know if it was nanoseconds or milliseconds or something very small, but some guy going around in a jet around the Earth. And they synced up at the top wherever they started, went around, came back. Clocks were slightly different.
Yeah, that's crazy.
Yeah.
Well, I wonder if you have twins and one's like a stewardess. They're two ladies. One's a stewardess. Well, it could be guys. Guys can be stewards. And she is traveling. The stewardess is traveling their whole life.
Yeah.
Like for 50 years.
Difference.
What'd you say?
It's still negligible.
Yeah.
Otherwise, we would have noticed this already.
But they might end up being like 5 seconds.
Yeah.
Younger.
Yeah. I mean, I don't know the order of magnitude of how many flights a stewardess goes on and how much time that. I should be able to do that. That's called the Fermi calculation. Have you heard of that?
Yeah. Well, put that into a proposal. Get the government to sign off on that. Show that it scales.
Yeah.
And this could be huge for the stewardesses out there, you know?
Yeah. The older twin who always wanted to be younger.
Yeah. That's that's weird. Yeah, if you were a couple, I don't know. Yeah, it would depend on how much it changes. But if you were the older twin by like a minute and you always got crap from your younger twin, you could actually end up becoming the younger twin.
Yeah.
That's crazy. That is it. The weird part is still super weird to me. The paradox is weird too. Looking at the clocks
There's
and stuff.
There's a solution to the paradox.
There's a solution?
Yeah. Because it's physics. Something has to happen. Like it can't be both.
Oh, well, what's the solution?
The solution is that the one who traveled in the spaceship is the one that's younger.
Oh, yeah. Okay.
Because he is not in an inertial frame the whole time. He's not in the same inertial frame. he changes. When he turns around, he jumps frames. In other words, he accelerates, but even if it's instantaneous.
What if you just stop it before he turns around?
Then both of them, they're like, if this guy continues to move and this guy stays here, they both think that they're both right. They're both younger. This one, the other one is younger. To this one, the other one is younger.
And they're both right.
Both true. Because they're at two different points. They're two different frames, two different points in space. And that's sort of like what I was saying before, is there is no now. Like, time is different. There's no real way to compare time at two different places, two different frames, without coming together and being in the same frame once again.
Yeah, that's so weird. And that messes with like the law of non-contradiction, I think, where it's like, which one's...
No, because it's not a contradiction. I mean, I guess it is.
They're both younger, right?
Well, it's saying that there's no universal time.
Okay. So
if they ever came together, there would be one true thing.
So the reason it's a contradiction is because you're thinking about it from your own inertial frame.
About it as if you're like this being that sees all frames.
Yeah.
And that there's this universal truth.
Yeah.
And so you're like, oh, that can't be true. But at least in special relativity it is.
Okay. That's not so bad. That's not so bad.
Yeah. It's weird because what happens in practice is that as he's going, the twin on the rocket looks at the other guy. He's like, wow, his clock's going slow. And when he gets there, like he's just before he turns around, he says, okay, he's this amount younger than me. Right when he turns around, suddenly this guy's age jumps like by 4 years or something.
Mm-hmm.
And suddenly this guy's older by a significant amount than this guy.
Yeah.
And then as he's going back, this guy's clock is still going slow, but he started out older. Yeah. So by the time they get back, he's seeing his clock go slow the whole time, but he still ends up being older when they come together.
Okay. Yeah, that's so weird.
It's very strange. It's also very strange that the paradox part is always excluded from the the idea.
I think everyone's mind just gets so blown by the first part. They're like, that's enough.
That must be the paradox.
Yeah. Well, it freaks me out because there's so much good sci-fi in there too. Like you could, like two twins or whatever, and one accidentally hits the like approach the speed of light button and goes off this way and is like, oh shoot, and hits it back, and they're to them they've only been gone for a little while, right? But like, no, it's been 5 years for us, dude. And like the whole mission, you just ruined it.
Yep. Yeah, I mean that's happened in Interstellar.
Yeah.
For a different reason.
Yeah.
It was not speed there; it was gravitational time dilation.
Yeah.
So basically, the same thing happens when you're you're in a strong gravitational field. You don't have to be moving. You can just sit there and your clock would be running slow.
How strong would that field have to be?
Very strong.
So nothing we'd experience on Earth?
No. Well, I mean, we experience it to a very small degree.
But like up at like the North Pole, they're not experiencing time differently, are they?
Yeah, a little bit.
But okay, yeah, because everywhere, if I move over to that point, this can be different than this, right?
So
but like
I think it's true that this effect needs to be included for GPS.
Oh, okay.
I'm told that, but I've never done the calculation or seen it done.
Yeah.
Sort of things that people always throw it out. It's like GPS requires general relativity to some level to be accurate. But
because you're moving. Yeah.
I can't confirm or deny that based on my own.
Okay. Man, that's what's so. There's so many cool things about the world that's like, we just keeps surprising. Like you would not think that. You would not think that what we talked about, the speed of light, that doesn't make sense. But okay, now I get it. You can make sense of why it doesn't make sense. But like the same thing, it's just so odd that the world would be like that.
Yes.
And then something that's I'll just plug this book. If you're listening, I'm sorry, but I don't really like Rebecca Goldstein. I'm not sure of the pronunciation she prefers. But this book was awesome. It's called Incompleteness. It's about Gödel. Proof and Paradox of Kurt Gödel. And so it's a really good book. I recommend it actually because I don't like her and I still love the book. So
That's a strong recommendation.
yeah, well, she was talking about how people took Einstein's general and special relativity and Gödel's incompleteness theorems, and people would use that to promote like postmodernism. And both of them, she was saying, like, would not be about that because they were not actually relativists. They didn't like that. They didn't want their things to be used in that way. Both of them somehow thought that they were still promoting an objective view of reality and, well, getting closer to the truth, the objective truth and stuff like that. But I thought that was so interesting to think because you hear like general or special relativity gets picked up by the woo-woo folks and they're like, and this is why our consciousness changes the universe. And you're like, well, I don't know, dude. I'm not sure if you are qualified to talk about that.
Yeah, that's, quantum mechanics is also dangerous.
Yeah, you're right. Well, dude, as we finish up here, like, did Einstein play any kind of role in your wanting to study physics or not really?
Yes. Not necessarily the person, but his work.
Yeah.
So I think one of the first times I got like excited about anything that was academic related, other than my high school physics class, I really enjoyed it. Like I had a bunch of fun.
Mm-hmm.
But then like I was reading, like, I think it was A Brief History of Time by Stephen Hawking.
Okay.
Like I'm not necessarily a huge fan of Stephen Hawking himself, but
yeah.
his that I really enjoyed that. Like I understood special relativity for the first time, and my mind was blown. Like I was working at the movie theater at that point, and I came in and I was trying to explain to everybody that I worked with special relativity, and I was just like, you guys, you gotta understand this. It's gonna blow your mind.
Yeah.
And yeah, so I got really excited about it. But in terms of Einstein the person, I actually, like, the most I know about, I didn't really know that much about Einstein until my roommate a couple years ago gave me a book on Einstein and Schrodinger.
Okay.
So I know a little bit more about Einstein.
Yeah. Okay. Do you know anything about like Schrodinger's cat kind of stuff?
Yeah.
Can we talk about that really quick before we?
Yeah. No,
okay.
I have plenty.
So what I've heard was that Schrodinger was like he was trying to show an absurdity and say like if you were to follow this and this and this, and we'd have to say this cat is both alive and dead, but we wouldn't say that, right? So let's not do that. But on the popular level, everyone goes, so there's this cat and he's both alive and he's dead in a box. Can you let's like lay it out for us?
You mean the whole Schrodinger's cat thing?
Yeah. Are you able to do that or?
Yeah. So it's the idea is that I might get the exact details wrong, but the idea should be correct.
Okay.
So there's like a jar of poison.
Uh-huh.
And there's also some radioactive element
Yeah.
in a box, and there's a cat. Hopefully it's the cat that's upstairs because nobody likes that cat.
Yes.
And it's radiating. So this thing is radiating. Well, radiation is in general, it's a probabilistic thing. Like it's not like, oh, it radiates exactly at this time all the time. It's just like, oh, it might radiate now, or it might radiate a little bit later, or a little later. So you're always just kind of waiting for it to emit something.
Okay.
And so the poison is set up just so that if it gets radiated on, it'll break, and the poison will hit the cat and it will die.
Okay.
And so then the idea is that you're in this box and there's no way to look inside the box or hear it or anything. There's no way to observe.
Mm-hmm.
And so at any particular moment, you have no idea whether the poison has been released or not. So it's essentially the cat is both alive and dead until you open the box and figure out whether it is. Actually, I think about this in terms of prayer all the time.
Okay.
Like if you're praying for somebody, but like the thing that you're praying for has already happened, but you haven't observed it.
Yeah.
It's like Schrodinger's prayer.
Yeah.
Like, oh, I hope they do well on their exam or something, but they took the exam like an hour ago. You just haven't heard whether they've done well.
Yeah, or
like, is there still point in praying about it?
Right, or if you're in different time zones, right? That's when I think about it a lot. Where I'm like, oh shoot, I said I was going to pray for this dude. I just realized that happened like 2 hours ago.
Yeah,
and some people will be like, well, no, I believe in B theory of time, and I think that God honors my prayers, and there's backwards causation. So God did know that I was going to because He's omniscient, And so he attributed that prayer towards him moving and helping this guy on the test. I don't like that. I don't like any kind of backwards causation,
Yeah.
but it makes you feel kind of nice if you forget to pray for somebody.
Yeah.
Yeah. Okay. So, do you remember like why
Yeah.
did Schrodinger what was the impetus that like motivated the
He
experiment or
hated
the
his
thought
own
experiment?
equation. Yeah, he hated his own equation. He
Okay.
came up with the Schrodinger equation. I think he was skiing with his 7 mistresses or something.
Dang.
No, he didn't have 7 mistresses. He had like a wife and a second wife. He
Okay.
had a whole like relationship with this other couple or something where they were just cool with each other in
Yeah.
that way.
Yeah.
And so he had this equation, and he wanted to describe quantum mechanics in a completely deterministic way, and he thought that's what it was going to do.
Yeah.
And so he solved the equation, and he found that it was this wave thing. And he said, "Oh, great! So these electrons are these solid wave things, and I know it at this time. I know what the wave does at this time. So at a later time, I'll know exactly what the wave is doing. So it's completely deterministic." But then other people like looking at the equation, and they're like, "Oh, actually, this wave thing, it's a probability function. It's not a physical thing. It's not like just a wave going around. It's this: the electron has a chance to be here or has a chance to be here, and it's always essentially probabilistic." And he hated that so much.
I hate that too.
And
Yeah.
so he created that example. At least I'm told. Never trust a scientist to tell you the history of science.
Okay.
I'll say that because they always try to put it in a way that makes the most sense, not
Yeah.
the way that's the most true. Because
Yeah.
history is never logical and easy to.
Oh, it's full of a bunch of crazy people.
Yeah, but if you
Yeah.
hear it from a scientist, it sounds like everything just happened, like, and then this happened, and this
Yeah.
happened. It's all this logical progression. But yeah,
Right.
so from the history of science perspective, it's like, okay, this is ridiculous. It can't be probability, and here's why with this cat example.
Yeah.
That's ridiculous. And Einstein was on board. So him and Einstein became friends because of this. Until I think it was Schrodinger stabbed him in the back. Because they were both working on a theory for like everything.
Yeah.
And they were communicating about it. And then Schrodinger just went to the press at one point.
Dang.
With it.
Dang. Well, was Schrodinger. Do you know about the I forgot what it's called. I think it was at Princeton. It was at Princeton, the Center for like Advanced Study or something like that.
IAS, so the Institute for Advanced Study.
Yeah.
That's where he was.
Was Schrodinger there?
House. No, that was Einstein.
Yeah, okay. I know Einstein was there, Gödel was there, like von Neumann was there, all these crazy dudes, which is insane. But I guess was Schrodinger, where was he from? Was he Swiss?
Was in the Ireland equivalent of the IAS. So they had an institute that was created to be the IAS for Ireland. Oh. And Schrodinger was the big catch. He was like the head of it. But this was after he created the equation. And he basically spent his whole rest of his life trying to live up to his reputation at this IAS by coming up with a great theory of everything. No.
Okay.
Both him and Einstein were trying to do the same thing.
Bro.
By the end of their life, they were just like, nobody was paying attention to them anymore.
That's what Kurt Gödel did as well. He came up with his incompleteness when he was like 23 or something. And then, well, he was like a real perfectionist. So I guess he did come up with some other stuff, but he never published it, never told anyone about it. And then he died from like starvation because he had all these like phobias and he thought someone was poisoning his food, which is tragic and horrible. But yeah, all these dudes like 23, 18, whatever, producing, and then they can never accomplish anymore, which is like, whatever, dude, they accomplish more than that.
I mean, that's why I'm so happy that I never accomplished anything great.
Yeah, that's great. I don't know. You put out
that's why I'm so happy.
You put out a COVID video, or like a video about a doctor singing. That might be your bar that you're never going to pass.
Yeah. No, I think my peak was my exit seminar, which we don't have thesis defenses. We just have like exit seminars where you present your research.
I watched that. Yeah.
Oh yeah. Well, did you see the end?
I just heard people laughing and then a bunch of just nonsense words and then people laughing and I was like, he's killing it, but I don't know what he's saying. But
no, at the very end, I broke into song.
Oh, I didn't see that part.
I sang a whole parody of American Pie. It's like 8.5 minutes long, but it's called My Berkeley in Time, and it's about me graduating. People said they got really sad because they're like they remembered their graduate student time and how they felt when they were leaving.
Oh, okay.
But I feel like I'm never gonna top that. Like that was
it.
I
Well,
should
it's
just
recorded. At least it's recorded, dude.
yeah.
That's you can put that out there. That's awesome. Well, dude, this was mind blowing as always. You got to come back on and blow my mind with
Oh,
some more stuff.
100%. Just like so, the thing is, there's a lot of random things that if you ask me about, like at a random point, I will have no idea what you're talking about. But if you give me like a week, I'll
Yeah,
be able to figure out what it is.
I love that.
It's
I
sort
love
of
that.
like not to compare myself to Iron Man, but I feel like every graduate student, like if you give them something, they can figure it out in like 3 days.
Yeah,
Like it'll just they'll be like you know the scene in the first Avengers where like Robert Downey Jr. walks in and he's like blah 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 something science, and they're like, when did you become an expert on nuclear astrophysics? And he's like, last night.
yeah.
And then like every grad student can sympathize with that because it's like, oh crap, this code is written in Fortran. I never knew anything about Fortran. 3 days later, they're like, Fortran.
I mean, I don't think I could do that. I'm a graduate student or whatever, but
3 days is an exaggeration, but like you give them like a week or a couple.
you're in like research mode and you're like,
Yeah.
I'm gonna do it. Actually, dude, I don't know a ton about different generations or whatever, but I know a lot of the millennials that are scholars right now, and I love millennials because we like want to know everything and we'll talk about whatever. So like my millennial guests are usually my favorites because I'll ask them something beyond the scope of their research or beyond their expertise, and they're like, I really don't know, man, but let me take a stab at it. And it's like, yes, do you like that's what we're supposed to do. And a lot of the older dudes who I love still, they're like, you know what, man, that's kind of outside my thing, and I'd rather not, step on a rake or something.
Well, they also have a lot more to do. Like they have responsibilities. I don't have responsibilities yet.
That's yeah. Well,
like
and we
take care of, and
we like to step on rakes too.
See, I don't have like any significant other, so I can do whatever. I have time for stuff.
Well, if you start singing this, man, people are gonna get sad again. You're talking about how you don't have responsibilities. Well, maybe you'll meet your wife through this. That would be fantastic. If you're out there listening, I mean, this dude.
It's your wife. Look at me.
Yeah. He's
If you like Dragon Ball Z too, yeah.
Oh, okay, dude. I know some scholars who are into Dragon Ball Z now, which is wild. So we're gonna wrap this up here, but Sean's gonna come back on and we're gonna get our mind blown some more. I hope you guys like this one. I liked it. I'm gonna have to go back and listen a little bit more. But this has been Parker's Pensées, and as always, all glory to God.